Hello, and thanks for stopping by. My name is Joseph Geringer, and I'm a materials development engineer here at Essentium. Essentium provides industrial 3D printing solutions that are disrupting traditional manufacturing processes by bringing product strength and production speed together at scale with a no-compromise engineering material set. Essentium manufactures and delivers innovative industrial 3D printers and materials enabling the world's top manufacturers to bridge the gap between traditional manufacturing and machining and embrace the future of additive manufacturing. We hope that the following information will be helpful for you and encourage you to visit our website at essentium.com. The webinar will begin shortly.
My name is David Riemann. I'm an applications engineer here at Essentium and will be your presenter today. Today's webinar is titled An Introduction to Blow Molding Production Using Additive Manufacturing. Blow molding is a widely used and inexpensive manufacturing process for a variety of polymers and applications, from bottles to automotive and aircraft ducting, to double-walled parts and more. In this webinar, we will be looking at how you can leverage additive manufacturing to enhance blow molding capabilities across 3 use cases, exploring the material selection, design, slicing, and post-processing needed to produce high-quality tools for blow molding. We encourage you to submit your questions through the chat feature, and we will address those during the Q&A time at the conclusion of this presentation. This webinar is being recorded and will be sent to attendees for future reference. We will now begin. Next. So a bit about myself. My name is David Riemann. I have 6 years of engineering, design, and manufacturing experience. I have 3 years of additive design and manufacturing experience specifically. Before coming to work here at Essentium, I worked at FedEx with an aircraft structures background. And then I transitioned into a different role where I was involved in a lot of pilot projects exploring the use of additive manufacturing to fill gaps and to supplement traditional manufacturing. Next. So today, so for a quick overview of what we're going to be working with today, I'm going to be giving a brief introduction to blow molding technologies. I'll be going over how additive manufacturing can be used to supplement that blow molding manufacturing, addressing advantages, disadvantages. I'll be giving a brief manufacturing comparison in one of the use cases, and we're going to be looking at the design, material selection, slicing, and post-processing for 3 use cases: a soda bottle, a double-walled chair with a metal insert, and some automotive or aircraft ducting. Next slide. So what is blow molding has been around for a while. It actually, in its simplest form, is sort of the natural evolution of glass blowing. The first step that started getting blow molding running was in 1933. Low density polyethylene, LDPE, was invented. It wasn't manufactured and built until about 1938, where the material was much more amenable to the blow molding process. So in 1938 is when the very first blow molding machine is produced and able to start producing parts. And it doesn't really take off, though, throughout the 40s. In the 40s, it just sort of, there's a few people that are using it, but for the most part, it is actually, it's not quite very popular. In 1953, high-density polyethylene is invented, and that's what really kicks off everybody being really interested in blow molding in terms of how it can be used for a variety of different products. That's where the industrial blow molding machines were first developed in Europe. And then those machines came to become available in the United States in around 1958. The first applications were, actually was in the United States was was a machine that was bought by Empire Plastics to make toy bowling pins. Toys were the first. Toys were the first. Were the first use case, really, and then also bottles as well. And then as this popularity for this technology increases in the 1950s, we start to see more and more patents coming out and more materials. In the 70s, they are able to make a biaxially oriented polyethylene terephthalate, PET, was developed. And that's really what caused the blow molding to take off and become as ubiquitous as it is today. In fact, from 1977, when you get the one-step process or the three-stage process for blow molding with preforms, you really start to see just the ubiquitous adoption of this and what led to a large number of the adoption of blow molding. And then also during the 70s, we have multi-layer blow molding that comes out, and that's what allows us to do different types of plastics within the same final product, so that you can, that was introduced with a ketchup bottle, and that allows us to control the different properties, whether or not it's going to be exposed to foods, or if you have a specific need for your blow molding purposes in terms of whether or not you need a stiffer material or a flexible material in different parts. And that's where this multi-layer blow molding pops up in the 70s. And even today, more materials and the advent of microprocessors and newer materials really allows the technology to take off. And today it's still widely used and continuously being improved with new robotics and new forms of blow molding like 3D suction blow molding. Next slide. So here is a breakdown of the different types of blow molding that we have. The most common is extrusion blow molding, where you can where the material is. I'll get that in my next slide. But some of the main advantages of blow molding are that it's got very, very fast production rates. You can mold very complex parts at a relatively low tool and die cost. The molds will generally last the lifetime of your production cycle, as there's a lot less wear on blow molds as compared to injection molding and other plastics manufacturing. There's a relatively low cost of high volume production parts, and the parts can be produced with a high strength to weight ratio. Parts can be reinforced with a lightweight foam core or internal ribs sometimes. Some disadvantages for blow molding is that you are limited to creating hollow parts. It's difficult also to control wall thickness, and you have to have really great care in your design and your equipment operation to ensure that you get as close to a uniform wall thickness throughout your part as possible. Compared to injection molding, you do get poorer surface quality on blow molded parts. And that's why when we get to this later, post-processing is going to be such a key factor for anything that is concerned with blow molding. Next slide. So this is the basics for extrusion blow molding. On the left, you see a picture of the basics of it. The resin comes in, just like with any typical plastics. And much like injection molding, it gets heated up and forced along an extruder screw, and that takes it to the die head. And at this point, the molten plastic is forced out through this die, and it creates an object called the parison. And the parison is just a hollow tube of really hot heated plastic, and that is what gets grabbed by your molds. That's what the diagram on the right is that you can see the sort of the four-step process where the parison drops down, the mold grips it, and either through the top or the bottom, or sometimes even a hypodermic needle, air is inflated into the parison, and then the mold and as the air comes in, the part cools, and then the molds will release, and the part is ready to be used. Next slide. So the next type of blow molding is probably the one that everybody is the most familiar with. This is the process that makes all the soda bottles, all those PET bottles that are all throughout the world. And in this, much like that first step where the resin is melted, instead of being forced through a die head like it was, it actually forms something called the preform. And some manufacturers produce a lot of preforms that can then be bought and used, and some machines also will have the preform as part of the entire assembly line, where it will make the preform, rotate it over into the blowing phase, and then into the cooling phase for ejection. So you can sort of see here that on the left side we have the preform, and then it gets grabbed into its mold. It's either, if it's a machine that has the preform making as part of its process, it can oftentimes still be plenty warm it has enough residual heat to where it doesn't need to be heated up. But if it's a preform that's been purchased, then it'll also have to heat that back up. At that point, then the core actually stretches down and stretches the part further. This helps to help really create that uniform thickness that produces a really good clean bottle. And then after that stretching, then the air is forced into it to fully expand it, and then the part is cooled and ejected and released. Next. And injection blow molding is essentially the same process. It just does not do that that stretching part, where it just heats up, or it takes residual heat and applies the air to produce that. This is the least common form of blow molding. It's limited in terms of its part size. You're typically producing really light parts. Oftentimes have they're a lot of times used in automotive purposes or in medical devices for small little medical bottles. These are small, less than 100 grams, maybe 20 centimeters, 10 centimeters in diameter, 20 centimeters long at most. And they're made from a single layer of material. Compared to extrusion blow molding, the tooling costs on a cavity basis for this type of molding are a little bit higher, since core rods and injection molds are all necessary for this process. This is also limited, as well as the injection stretch blow molding, to where you cannot produce anything with a handle. It all has to be a fully enclosed volume for it to be able to really work. Next slide. So where does additive manufacturing fit in with the world of blow molding? So there are some advantages for using additive manufacturing to produce the molds for blow molding. Those advantages include being able to start printing as soon as your design is finished. A lot of times with traditional mold manufacturing, you have to work on a design team, go out to a manufacturer if you don't have a machine shop on your own, wait in line and wait until you get that process to happen before you can start to see your work. With additive manufacturing, when you have a 3D printer on site, as soon as you have a good idea for a design, you can go take it out, and depending on the size of your part, you could have it within, a few hours to, just over a day. There's also a lot less machining time. When you produce a part from an additive manufactured mold, all you have to do is just clean up those surfaces in order to get a nice, really clean surface. You're not going to be using a lot of machine time to fully cut out all the features on the part. And then the other biggest advantage is that the materials that you would be using for an additive manufactured mold are going to be a lot cheaper than the tool metals that you would typically use, like aluminum, or in some instances steel, for the blow mold. So those are the three real big advantages for why you would want to use additive manufacturing to help supplement your blow mold manufacturers. Some of the different disadvantages for additive manufacturing is that you do have a poorer surface quality. Like I said a moment ago, you're going to have to do some post-processing on it, because you're not going to have that really smooth surface that you would get from a CNC right out the printer. So you do have to address that poor surface quality. That's going to be the first thing that sort of rolls into there's going to be a necessity for post-processing. The other thing is that there's going to be longer cycle times because of poor heat transfer. When the molds close around the parison, a typical mold cooling time, depending on the application for extrusion blow molding for a bigger part, might be about a minute or so. That time probably gets bumped up to 80 or 90 seconds because these are plastic parts instead of metal molds, and so they have that very poor heat transfer. Because of that, also, you're limited in terms of how many cycles you can run. You're not going to be able to run these back to back like you would with traditional manufacturing, because you can't run coolant lines through the plastic parts, and you'll have to basically let it air cool. So you might run a couple of cycles, let the molds separate, and blow some colder air on them to help with that, because again, the poor heat transfer properties for plastics. Next slide. So as I was mentioning just a moment ago, you can't run cooling channels like you typically would. A picture on the right just shows some examples of typical cooling channels that you would see in your metal aluminum molds. And with the additive manufactured parts, because they aren't watertight with the printing with fused filament fabrication printing, you can't create those cooling channels in there. It would leak into the mold, and it wouldn't be good for you. So because of that, you've got those longer blow times, and you've got to periodically cool off the mold surface with air. And so that's definitely one of the things that you have to keep in mind, consider when you are designing and exploring the possibility of using additive manufacturing for your blow molds. Next slide. So I'm going to go ahead and jump into post-processing. It may seem a little counterintuitive that you would want to address the post-processing before getting into the design, but it's actually going to have a straight direct correlation to some of the design decisions that you have to make when you're doing your additive manufactured molds. So you really need a clean surface for a good quality blow mold produced part. The biggest area of concern after that nice, really clean surface is going to be the parting line and the pinch point of the mold. What we're seeing is that because these aren't metal, or I'll get to that in a later on slide. And this also directly affects how you're going to design the size of your part, of your mold. For traditional manufacturing, a lot of times you might get your desired part and then maybe scale it up by about 4%, or point, just, a very small amount to account for the shrinkage that occurs naturally as a part of the plastics during their cooling cycles. With additive manufacturing, you are going to sort of want to go in the opposite direction, where you might shrink the part down because you are going to need that extra material that you can then machine away and get down to a clean surface. You don't want to start at your desired size. Just for example, you wouldn't want to start, if this was going to be your final part, you wouldn't want to start with this. You would want to scale this down ever so slightly to give yourself a few extra millimeters of material that you could then machine away so you can get to a nice clean surface. And that goes on to what the best process is for post-processing these additive manufactured parts, and that would be with traditional CNC machining. You can take a look at, if you go to the next slide, please. Here you can see some what a part that's already been sort of tumbled. I've also got it here. If you can't quite tell in the pictures that are on the slide, this has just been tumbled in a media tumbler, and it did create a much smoother surface all around for this part. But because of that constant tumbling and bumping and grinding that created a smooth surface, it also wore down the parting line. And you can sort of see that in the two pictures on the left there, where you don't have a really clean and sharp surface. And so the picture on the right sort of shows what that would result in terms of your part. On the picture on the right, on the left side of it, that's sort of the ideal, where you have a nice, really crisp and clean, sharp corner right there, and a nice, good flush mate. So that way, when the object is blown, the persona is blown to produce your part, you get a really good and clean flush parting line, where you don't have any defects or anything like that. If you were to try and take this tumbled part, you'd end up with something sort of there on the right, where you have almost like a little dip or a cavity, where once that parasol starts to expand, it's going to want to sort of fill in that void, and that's going to really produce a bad quality part. It's going to introduce some defects, possibly even, and it's not something that so that's why traditional CNC machining is going to be the best solution for producing a great part. Let's go ahead and sort of jump back into some of the design things to keep in mind when we're trying to design parts for our blow molds. If you go to the next slide. So some general design rules. With blow molding in general, you have the parasol comes down and it's got a nice uniform thickness to it for the part. What happens when it starts to expand is that it will, catch whatever is there first, and then it will sort of pull and slowly stretch to fill all the rest of the voids. You can see here sort of a progression of what it would look like for when a parasol comes in and sort of fills in those voids, where depending on the design of your part, you have issues where it's the walls get so thin that you might have a potential blowout, and so it's and you have an ununiform thickness throughout the part, so it creates a lot of possibility for defects and a lot of issues. So that's why blow ratio is a really big important part for designing it. There are a lot of different formulas to account for how to calculate your blow ratio. But a lot of times with the modern machines, that blow molding machines that we have today, there are tools to help you calculate what your blow ratio is to make sure that you've got a nice, clean, well-designed part. Next slide. Here you can see one of the this is for designing the pinch off. Because of the really high, comparatively high pressure and mechanical stress exerted on the mold bottom when it goes in that closing step, it pitches one end of the parison together. This pinch off is usually made out of a metal metal portion, and with additive manufacturing, you can also leave sort of a void in your mold to put in a metal pinch off if you would like to. And then typically a good size is about, 5 thousandths to 15 thousandths of an inch, or 0.1 to 0.5 millimeters gap right there. And it's really important to try and keep those pinch off designed very well. Otherwise you get, a really bad pinch off, and you can see that on the bottom there at the right, where if you don't have that well-designed pinch off point, you're going to run into issues with part quality. Next slide. So we're going to also take a look at some materials that we will be using to create these molds. PET, in terms of where PET is at its melting point. PET has a relatively low melting point compared to other blow mold plastics like polypropylene and PVC, etc. And so when we're looking at PET, we can probably go with something that's going to be a little bit less expensive, but still have good heat resistant characteristics. And so we're going to be looking at probably carbon-filled polyamide, PACF. That's going to be a great candidate for working with for bottles and PET. For if you're running like a polypropylene, those will sometimes be extruded at around 210 to 218 degrees Celsius. And so we're going to be looking at HTNCF 25, a high temperature nylon that's also got a carbon fiber fill of 25%. And these are other materials that Essentium offers that have other great properties. And what's good about the blow molding, because of the lower temperatures and lower pressures, you can really take advantage of being able to use a less expensive material, as opposed to if you were trying to do injection molding or if you had other applications where you needed a more expensive, high heat, more exotic material. Next slide. So as I mentioned, this is just a simple bottle design that was thrown together for the purpose of sort of walking through the slice settings for our first use case. As I mentioned earlier, the PET bottles are some of the most widely used applications for blow molding. Plastic bottle production by blow molding manufacturers has drastically changed the environment of the earth. Production has grown from 0 to over 10 billion pieces in just 20 years. And so we're going to be taking a look at using that carbon-filled polyamide, that PACF, to create the mold for this part. Next slide. So on the left, you can see the CAD model for this part. What you see on either side of the main volume are vents. one of the things to keep in mind when you are designing your molds is that as the parasol is being blown to expand to produce your part, the air that's inside that mold has to go somewhere. And so vent lines are drawn throughout the mold. And they're typically at the deepest part where the deepest part of your mold where the material is going to sort of reach last, and it'll be forcing all that air out as it goes there. On the right, you can see the mold as as it has been as it's been sliced and simplify. And what I used for my slice settings are I used 20 top and solid. I sliced these with a 0.8 millimeter tool head, and so that's got a layer height of 0.3 millimeters. And to get a good solid 6 millimeters or so of solid surface, I went with 20 top and 20 bottom solid layers, and I'm running 8 perimeter shells to produce a really strong part. I also ran this at 50% of 50% infill. With the bottle, you could probably get by actually with being able to produce that at a much less infill, because the injection blow molding compared to the extrusion blow molding sees less pressure and will probably be amenable to being able to use less material. The estimate that I got for how long it would take to print this was only about an 8-hour print at that, like I said, with those 20 top and bottom layers, 8 shells, 8 perimeters, and 50% infill. And so being able to go from your design to a possible, finished mold in about 8 hours, plus a little bit of extra time for machining, and you can sort of start to see where additive manufacturing has its role as a rapid prototype, or as a as as a way to do these sort of exotic or boutique molds, where you don't necessarily want to spend a lot of money on a traditionally machined mold where it might have a relatively low quantity run. And then next slide. So here is another example for a part that we can produce. This is a double-walled part. It's going to be like a seat. And not pictured here is that at the bottom of this part, there are going to be 4 threaded inserts in it to allow you to attach it to a metal frame. And what's great about being able or what's one of the things that you can take advantage of in blow molding is that as the parasol gets blown and expands, it will be able to actually grab around things that are in its way. And so this is a very common practice. So there are threaded inserts that are designed like the picture on the left with extra features, a little bit of like a bigger base, so that as that parasol is blown in after it's heated up, that it grabs onto and holds those threaded inserts in place, so that you can then have some better mechanical properties for the part. Next slide. So blow molded hollow parts can be modified for specific use cases. Parts can also be filled with polyurethane foam or expanded beads of polystyrene. You can get benefits for kinetic energy dissipation and deformation resistance. This is done a lot of times in the automotive industry with filled bumpers. And you can also adjust the sort of the comfort even of the part in terms of how much give it can have. And so you've got there's a lot of areas where double-walled parts can be modified and adjusted to where you can run very far with how you design it, and you can really push the limits of that with additive, where because you have this a plastic part that you can do, or that it costs a lot less money and has a lot less time to produce, you can experiment a lot more when you have an additive produced blow mold part, as versus having to wait and spend a lot of money to get a traditionally machined part. Next slide. Here you can see in the middle a quick slice of it. These are, again, I kept the same settings. At the top of on the left side of the middle picture, you can see where I have the start of my parting line and my pinch point to catch all the flash. But you also see those crash pads at the top left and top right of the part. On the very left side of the screen shows a slice a few layers down beneath those 20 top and bottom layers, where you can see the infill. What the crash pads do is that as the molds come together, in order to keep some of the pressure more evenly distributed so that it's not all entirely pressing on that pinch point and possibly even damaging that thin piece of material, you want to sort of help distribute the load. Because even though the pressures in terms of what the Parason is putting on the part when it's being blown is fairly low, what you do have to keep in mind is that the molds have to be pressed together at a pretty high pressure, and so they need a lot of strength there. And as the Parason is blown out, the molds are going to want to release. They're going to want to pull apart from each other. So that's why the blow molds will oftentimes add even more pressure during the blowing process to make sure that those molds stay together. So rather than damaging that really fine pinch point where it's got a really thin edge to help produce a nice clean flash that you can rip away easily, you want to have those crash pads to help distribute the load. But because of the higher pressures, you want to have a solid basically all the way through the part. With Simplify, there's a couple of ways that you can get around this. On the left side, you can see that that's just a regular sliced crash pad with 50% infill underneath it. It's all right. It probably could withstand some of those pressures, but rather than risk it, you can see on the right side that I have a fully solid crash pad on that side that goes all the way down to the part. And I was able to achieve this just by getting a 10 micron slice basically out of the part. What this has done is it creates basically separate solid bodies. And so you can see on the right side, it looks like almost like Russian nesting dolls, where it's just a bunch of walls inside of each other all the way down. And that 10 micron cut just gives it a nice clean parting line. It creates separate bodies, but it still allows you, when you print it, it's still basically pressed up against each other, and it produces a fully solid part. It's just a way to sort of trick the software in order to produce that nice, really solid footing all the way down to help distribute the load without worrying about having to damage anything. Next slide. And before we do that, you can see in the middle where there are 4 pegs standing up, and that's where the operator would take those threaded inserts and place them on top of those, and those will hold them in place so that when the parasong goes around it, you get you get those threaded inserts fully embedded into the part, so that you can then have that fastening hardware that you can use for other purposes. Next slide. So then we can also take a look at automotive and aircraft ducting. The part on the left there is something that I've just sort of thrown together as an example of what you could do. And then on the right, we've got a part that is 500 and it is 610 millimeters by 350 millimeters by 100 millimeters. So it's a really big part that we can produce on our machine here, and that there are other fuse filament fabrication machines out there that can also produce similar sized parts. If we go to the next slide, again, you can sort of see here the importance of the post-processing. You can see on the picture on the right that you have those where the curves are, because again, this is being sliced with a 0.8 millimeter head a 0.08 millimeter head in order to produce a really a faster printing part, because otherwise it would be even a part this big is going to take a lot of time, and trying to slice it with a smaller nozzle would you would get a cleaner part quality surface finish. However, you have to weigh that against how long it's going to be in there printing. And this part is so you can see on those curves as it's coming up, it creates that tiered effect. And so this is where that post-processing is going to be very important, and why you want to go to traditional machining to do that. You could possibly, go in with hand tools and try and sand it down yourself, but you're going to get a much cleaner and a much higher quality finish with traditional manufacturing. And next slide. So as I mentioned, that duct mold was about 610 millimeters by 350 by 100. A similarly sized part in aluminum would probably be about $20,000 to $25,000 with 4 to 5 weeks of lead time. Because this part was imagined as being like a polypropylene duct, we went with that HTNCF. The amount of material was roughly like 12. It was at 12 kilograms after the final slicing, and that's just because, again, it has that 6 millimeter shell all the way around it, those 20 top layers, those 20 bottom layers, and the 8 perimeters for the part, as well as those fully solid crash pads, on all the corners and in the middle to help evenly distribute weight off of that pinch point. And so the print estimate that I had for this one was going to be a 3-day print per mold half, and maybe probably 1.5 days of post-processing for the second half. So after 3 days, you get that first mold half. You can then give that to the machine shop and have them start doing the post-processing, cleaning up the surface finish and making sure you have a nice, really clean parting line and pinch line. And then you can also, while they're machining that, you can also go and have your second mold half printing. And so roughly 8 days and, $10,000 worth of material and post-processing, you've got a much less expensive part and a much faster part to be produced. Because if you would want to, pay for rush to get a similar aluminum part made, you'd have to, pay probably an extra $10,000 or a little bit more to get down to a similar time for aluminum. And you really start to see these cost benefits where if you have a really big part, that's where you start to really see the advantage of using additive manufacturing, because the bigger the part, the more money that you save on material, and especially with how long it would take to source that from a traditional manufacturer. That's the real advantage for this additive manufacturing for blow molding. Another thing to point out that I'd forgotten to put in one of my slides is that typically you might have a pinch point for a parting line to be maybe 80 thousandths wide to when it's made out of typically metal. But again, because of the poor heat transfer for these additive parts, what I was playing around with was sort of doubling that up and creating an extra like 160 thousandths essentially wide, 160 thousandths, so about 3 millimeters wide, 3 millimeter wide pinch point for an additive part as versus versus traditional manufacturing. Next slide. So in conclusion, where additive manufacturing and blow molding go together is that you get a huge reduction in time and cost. It's ideal for prototyping and low quantity production when you have those possibly like parts that aren't made anymore, that would cost a lot of money to try and go back to the OEM and have them produce, or to try and or just a very small production run where the benefit of having a traditionally manufactured part isn't worth it just because of the cost of it. You can really see the benefits where additive doesn't replace traditional mold manufacturing, but can help supplement it, and allow us to sort of to really explore everything that we need. So at that, I'll go ahead and open it up to questions. Yes, the slides will be made available to I know that this recording will be made available to everybody. I will check with the team to see if the slides will be made available as well. What if you used a metal-filled plastic part to increase the heat dissipation of the mold? That is a great question. That is something that you can explore. You would still need to do that post-processing to clean out the surface. The only hesitancy that I would have with that is that the real advantage for an additive produced mold is that you have that high reduction in cost. By going to a metal filled plastic part where if like you did like essentially a coating on it to help with the dissipation, that's going to be extra processes, it's going to be extra time, and so you'd probably be eating into a lot of the cost savings of an additive part as to add that metal for possibly not that much reward for the extra heat dissipation for the metal part. But it is something that that we've thought about and that we're sort of exploring as we take a look at how additive can be used with blow molding. So that's a great question. Thank you. How many cycles can a 3D printed mold withstand on average, and what's the cycle time? I think that I mentioned earlier that for a traditional extrusion blow molded part, a larger part might have a cycle time of about 60 seconds in the mold, and the 3D printing cycle time would probably be in the 80 to 90 second range. But again, you just run where you can't run them back to back to back like you would with a traditional metal mold, because there are no coolant lines, and because of that poor heat transfer, you have to just basically let the part air cool, or blow cold air over that part. I don't have information on how many cycles they can withstand. we have a lot of different materials here at Essentium. Others, like I said, I looked at PACF and HTNCF for these use cases, but we have a bunch of other materials. There's PPSCF has proven to be great at even withstanding injection molding, and being able to withstand several cycles with that. Since blow molding is a much less intense process, I would imagine that you would have a fairly long life for an additive manufactured mold. And again, because the advantage for additive manufacturing is for lower quantity parts, you would probably be seeing you would be using your additive manufactured mold for those low quantity runs. So it wouldn't probably see as many cycles as a traditionally machined mold for a mass production for a high quantity part run. If you have no blow molding capability, what's the startup costs for the blow molding equipment, not including mold costs? That's a great question. You can, and I will just refer you to some of the manufacturers. I've got two actually listed on the appendix on the next page that where I got some of the sources for in terms of information on blow molding, and as well as helpful design tips for generating these molds that I did that. And so that's going to be something that you would have to go to blow molding manufacturers or parts or blow molding machine manufacturers to get that information for that cost. FDM parts can be tightened by infiltration. Could this make cooling channels possible? That's something that we would definitely want to take a look at. It's what the beauty of additive manufacturing is that it's a very flexible technology because of the low cost of materials and the freedom of the machines in order to do a lot of different designs. You can play around with a lot of experimentation at very low cost of opportunity. You can do a lot more experimentation without having to worry about massive cost overruns or damaging really expensive equipment with additive manufacturing. You wouldn't want to necessarily experiment with a traditionally manufactured mold, and if you had an idea for what you want to do, because it is such a costly and time-consuming process to get that part. But with additive, you can definitely try basically anything you want with it, because if it ends up breaking it, you can just get a little bit more plastic and print some more, and continue to iterate on those designs. So it's definitely a possibility for exploring. Another question is, what do you see as an industry that would be a really good candidate for additive manufactured blow mold parts? As I mentioned earlier, I have a background in aircraft engineering, where I was a structures engineer for FedEx. FedEx flies a lot of older converted aircraft, passenger to freighter. And what I saw as an engineer then was that when those older aircraft had a part that broke and needed to be replaced, it was a huge process to get a replacement part from the manufacturer. Oftentimes, the original parts manufacturer has gone out of business, or there's a ridiculously long lead time where you might have to wait 200 days or even longer to get that. And so what I think that's great about additive manufacturing is that, especially for blow molding, is that instead of printing the part itself, which you can do, but right now you're only limited to using 9085 PEI, 9085 to actually produce a plastic part for an aircraft. But there are a bunch of blow molded components on aircraft, anything from like seat covers, armrests, ducting, and so you can use additive manufacturing to produce a mold that you can then send to a blow mold manufacturer, or if you have the capabilities to do blow molding yourself in-house, to produce that part without having to then go back through the OEM and face those high costs and those really long lead times. And so I think that especially looking at like legacy aircraft that have parts breaking as they age and the original manufacturer isn't necessarily around anymore, anything that you can do to get the aircraft back to tip top is always a huge advantage. All right. Well, thank you all so much for coming and joining us today. We hope this information has been helpful for you. This webinar is being recorded and will be sent to all attendees via email, along with more follow-up information to come about exciting news and events. For more information about Essentium, visit our website at essentium.com. Follow us on social media at Facebook, Instagram, Twitter, and LinkedIn, or you can email us at sales@essentium.com. Thank you for joining us, and we hope you have a great day.